Myself, Madhuri Modak, Assistant Professor in Mathematics, Department of Computer Science, Abhiday Namdar Senior College. Now, in the paper Groups and Coding Theory, we have seen first and second unit. Now, first unit was introduction. In second unit, we have seen definition of group and some examples of finite and infinite groups. Now, we start with the third unit, that is finite groups and subgroups. Now, next is permutation group. Composition of two permutations, representation as a product of disjoint cycles, inverse and order of a permutation, even and odd permutation. Now, what is permutation? A permutation on a set A is a function from A to A that is both 1, 1 and onto. So, 1, 1 is nothing but injective. It means distinct elements of A are mapping to distinct elements of A. Means no two distinct elements are mapping to the same element. Then second is it is onto. So onto means as it is a function from A to A, the from codomain A, every element has pre-image in the domain set A. So whenever we are defining some function from set A to set A itself, which is 1, 1 as well as onto, then that function is known as permutation. Now, what is permutation group? A permutation group on a set A is a set of permutations that forms a group under the operation of function composition. Now, see some remarks. The identity function, which maps every element of A to itself, serves as the identity element for this group. So, remember in permutation group, identity function acts as identity element. Now here we are considering A as a finite set of the form 1, 2, 3 up to n. Now see some permutations. Consider the following permutation alpha defined on the set A is equal to 1, 2, 3. Now actually on the set A is equal to 1, 2, 3, we can define 6 permutations. So that permutation is nothing but function from 1, 2, 3 to 1, 2, 3, which is 1, 1 and onto. So there are total 6 permutations that we can define. Now here the permutation alpha is defined as alpha of 1 is 1, alpha 2 is 2, alpha 3 is 3. It means 1 is mapping to 1, 2 is mapping to 2 and 3 is mapping to 3. So 1 and 2 are different element, their images are different. 1 and 3 are different element, their images are different. 2 and 3 are different element, their images are also different. So the function is 1, 1. At the same time, the codomain contains 1, 2, 3. So 1 has pre-image 1, 2 has pre-image 2 and 3 has pre-image 3. So every element in codomain has pre-image, that means it is onto. So this is 1, 1 onto function defined from A is equal to 1, 2, 3 to itself. So this is a permutation. Now we can express alpha in the form of array as follows. So the domain elements are 1, 2, 3. So we write them in the first row. And below that element in second row, we have to write their images. So image of 1 is 1. So we write it in second row below 1. Image of 2 is 2. So we write it below 2 as an image 2. And image of 3 is 3. So we write it in second row. So alpha I is directly below I for each I. Also inverse of alpha is the function defined by, now here as 1 is mapping to 1, alpha inverse of 1 is 1. Similarly as 2 is mapping to 2, alpha inverse of 2 is 2 and alpha inverse of 3 is 3. So alpha inverse we can write in the form of array as domain is 1, 2, 3 and their images are 1, 2, 3, which we have written as second row. Now see another permutation beta defined on the same set. Here beta 1 is 2, beta 2 is 3 and beta 3 is 1. Again see 1 and 2 are distinct element. Their images are 2 and 3 which are distinct. 1 and 3 are distinct elements. Their images are 2 and 1 which are distinct. 2 and 3 are distinct elements. Their images 3 and 1 are distinct. So distinct elements have distinct images means it is 1, 1. At the same time, codomain contains 1, 2, 3. So 1 has pre-image 3, 2 has pre-image 1 and 3 has pre-image 2. It means every element in codomain has preimage, so it is on 2. Now, how to write beta in the array form? Similar to previous case, 1, 2, 3, that is domain. So we write in the first row, and below that you have to write their images, as beta 1 is 2, beta 2 is 3, and beta 3 is 1. And how to write inverse? Write inverse, again the domain set is 1, 2, 3. Beta inverse of 1 is 3. So we have written below 1 as 3. Then beta inverse of 2 is 1. So below 2 we have written 1. And what is beta inverse 3? It is 2. So we have written it below 3 in the second row. Now, round brackets are also used to denote the permutation in array notation. So we can use either round bracket or square brackets to write the permutations in array form. Now, composition of permutations expressed in array notation is carried out from right to left by going from top to bottom and then again from top to bottom. Now see how to find composition of two permutations. This is alpha and this is beta. Both are permutations on some set A equal to 1, 2, 3, 4. Now alpha beta or alpha composite beta. For that, domain is again 1, 2, 3, 4. So first row is same 1, 2, 3, 4. Now we go from right to left and from top to bottom. Now beta of 1 is 2. Now we consider what is alpha 2. Now 2 goes to 2 here. So finally we write alpha beta of 1 as 2. Same way, whenever we have to find alpha or beta of 2, first we consider what is beta of 2. Now, beta of 2 is 1. And here, from right to left, 1 goes to 3. So, finally, 2 goes to 3. Then, beta of 3 is 4. And here, 4 goes to 4. So, finally, 3 goes to 4. And then beta of 4 is 3 and alpha of 3 is 1. So alpha beta of 4 is 1. So in this way, from going from right to left and then from top to bottom, we can find composition. If we want to find image of element 1, then first see that right hand permutation, that is beta. Beta maps 1 to 2, and then left side permutation, that is alpha maps 2 to 2. Hence, alpha beta maps 1 to 2. Similarly, we find images of remaining elements. Now, we define symmetric group of degree n denoted by Sn. Now, if you consider A is equal to 1 to n, then there are many permutations that we can define on this set. Set of all such permutations on A is called as symmetric group of order n or symmetric group of degree n, and it is denoted by Sn. Now, in particular, if n is 1, then A contains only one element. So, there is only one permutation, that is 1 goes to 1. So, S1 contains only one element. Then what is S2? Set of all permutations on A equal to 1, 2. Now, there are two permutations that we can define. In one case, 1 goes to 1 and 2 goes to 2, that is identity permutation. And in second permutation, 1 goes to 2 and 2 goes to 1. So, S2 contains two elements. And in S3, it contains the permutations defined on 1, 2, 3. So domain is 1, 2, 3. So in every case, first row is 1, 2, 3. And then 6 functions are possible, which are 1, 1 and on 2. So S3 contains 6 such permutations. Now, the important thing is that the order of the group Sn. So, remember, order of the group Sn is n factorial because it is nothing but arrangement of n symbols in a line. So, in how many ways we can do that arrangement? It is in n factorial ways. So, order of the group Sn is n factorial. See here, for S1 it is 1 factorial, which is 1. For S2, 2 factorial, which is 2 into 1, 2. For S3, it is 3 factorial, which is 3 into 2 into 1, 6. So, in general, order of Sn is n factorial. And this group is non-abelian for n greater than or equal to 3 because composition of permutations is not commutative. So, for n greater than or equal to 3, this group is non-abelian. Now, there are some examples here. This is sigma, which is a permutation on 5 symbols because in first row we observe 1 to 5 elements. This is tau. Again, it is a permutation on 1, 2, 3, 4, 5. Now we have to compute sigma square, sigma tau, tau sigma, sigma inverse tau. Now what is sigma in square? It is sigma composite sigma. Now similarly from going from right to left and top to bottom, we find sigma square. Now this is sigma, again sigma. So as it is a permutation on 1, 2, 3, 4, 5, the first row is again 1, 2, 3, 4, 5. Now right to left, 1 goes to 4 and then 4 goes to 1. So finally 1 goes to 1. Then 2 goes to 3 and 3 goes to 2. So 2 goes to 2. So in this way we get this as 1, 2, 3, 4, 5 in second row. Same way we can find sigma tau. This is sigma, this is tau. Now 1 goes to 3, 3 goes to 2. So here it is 2. Then 2 goes to 1, 1 goes to 4. So second element is 4. So in this way we can find tau sigma also. Now next part is sigma inverse tau. But for that we need to calculate sigma inverse. Now observe sigma. Now sigma inverse is again a permutation on 1, 2, 3, 4, 5. So that is our first row. Now here 1 is an image of 4. So sigma inverse 1 is 4. So below 1 we have written 4. Now what is sigma inverse of 2? 2 is an image of 3. So sigma inverse 2 is 3. Same way we get the remaining elements. So once you calculate sigma inverse, you can find sigma inverse 2 in the same way of composition. Now in above example, see, this is sigma tau and this is tau sigma. They are not equal. That's why the permutation group is not abelian for n greater than or equal to 3. Now cycle. Let sigma be a permutation in Sn. If there exists a list of distinct integers I1, I2, Ir such that sigma of I1 is I2, sigma of I2 is I3, sigma of Ir minus 1 is Ir, sigma of Ir is I1, which is the starting element, and then sigma k equal to k if k is different from I1, I2, Ir, means k is not in the set I1, I2, Ir. Then sigma is called a cycle of length r and is denoted by I1, I2, Ir in round bracket, either separated by commas or without commas. So here actually we must get some r distinct element I1, I2, Ir such that I1 is mapping to I2, I2 mapping to I3, Ir minus 1 mapping to Ir, and again Ir is mapping to I1 itself. Then in that case, and for remaining elements they are mapping to themselves identically. Then that sigma is a cycle of length r. Now, every cycle of length 2 is called as a transposition and cycle of length 1 is the identity permutation. Now, if A is 1 to 9, then the symbol 1, 3, 4 to 6 means a permutation. Now, see, as it is a permutation on 1 to 9, in first row we have written 1, 2, 3 up to 9. Now, this is one cycle because this is written in cyclic form. So, after 1 there is 3, it means 1 maps to 3. So, below 1 we have written 3. After 3 there is 4, it means 3 maps to 4. So, below 3 we have written 4. After 4, there is 2, means 4 maps to 2. So below 4, we have written 2. Then after 2, there is 6, means 2 maps to 6. Now after 6, the bracket closes. It means 6 will map to starting element 1. So 6 goes to 1. Now some elements from 1 to 9 are absent here, which are 5, 7, 8, 9. So they map identically. It means 5 maps to 5, 7 maps to 7, 8 maps to 8 and 9 maps to 9. So in this way, the permutation written in cyclic form, we can write it in the array form. Now, here sigma is given in cyclic notation, which is a permutation in S5. We have to express it in the array notation. Secondly, this is alpha written in array notation. We have to express it in cycle notation. Now, in third, beta gamma are given, and then we have to find beta composite gamma. Now, sigma is an element of S5. So, it is a permutation on 5 symbols. Now, as it is written in cyclic form, 2, 3, 1, 4, it means 2 maps to 3, 3 maps to 1, 1 maps to 4, and the last element 4 will map to 2. So we have written this as sigma 2 is 3, sigma 3 is 1, sigma 1 is 4, and sigma 4 is 2. Now as 5 is absent in this cycle, we can say that sigma 5 is 5. So we got images of all elements in 1, 2, 3, 4, 5. So just we rearrange it in the array notation. As sigma of 1 is 4, below 1 we have written 4. As sigma of 2 is 3, below 2 we have written 3. Like that we can complete sigma. Now this is reverse way we have to do. Alpha is already given in array form and we have to convert it into cycle form. So we start with the first element. Alpha of 1 is 4. Alpha of 2 is 1. Then alpha of 4 is 2. And 3 and 5 are mapping to themselves identically. So we get here as 1 maps to 4. After 1 we write 4. So 1 comma 4. 4 goes to 2. So after 4 we write 2. And 2 goes to 1. So we are getting again the starting element. So here we will close the bracket. So we get the cycle 1 comma 4 comma 2. And the remaining two elements 3 and 5 are mapping to themselves identically. So they are actually cycles of length 1. So we can omit these cycles. So alpha is equal to 1 comma 4 comma 2. So in this way we have expressed alpha in cycle notation. Now in third example, beta and gamma are given in cycle notation. So if they are written in cycle notation and we are using the same part directly, then it is difficult to find beta composite gamma. So if you express beta and gamma in array notation, then immediately we can find beta composite gamma. Now observe here, the maximum number is 5 and here also maximum number is 5. So you can consider beta and gamma as permutations on 5 symbols 1, 2, 3, 4, 5. Now this is beta 1, 3, 5. It means 1 goes to 3, 3 goes to 5 and 5 goes to 1. The remaining 2 and 4 map identically. Now here another gamma cyclic notation is 2, 1, 4, 5, 3. So 2 goes to 1, then 1 goes to 4. 4 goes to 5. 5 goes to 3. So below 5 we have written 3. And after 3 bracket closes. So 3 will map to starting element that is 2. Now from going from right to left and top to bottom we get beta composite gamma. Now, next definition is disjoint cycles. Two cycles I1, I2, IR and J1, J2, Js are called as disjoint cycles if the sets I1, I2, IR and J1, J2, Js are disjoint. Now, similar to two disjoint sets, as if they do not have any element common, here two cycles I1, I2, IR and J1, J2, Js are called as disjoint cycles if the cycle as a set I1, I2, IR and J1, J2, Js are disjoint sets. For example, consider the cycle 1, 3, 7, 8 and another as 4, 5, 2, 6. They do not have any element common. So these two are disjoint cycles in S8. Now, one theorem, any permutation sigma in Sn can be expressed as a product of pairwise disjoint cycles. Now, in this example, we have to express the given permutation as a product of disjoint cycles. Now, first is sigma. It is a permutation on 6 symbols. Now, sigma of 1 is 2, sigma of 2 is 5, sigma of 3 is 1, sigma of 4 is 6, like that we have given. Now, to write it in the cycle form, we start with first element, sigma of 1 is 2. Now, sigma of 2 is 5. Now we find what is the image of 5. Sigma of 5 is 4. Then image of 4 is 6, that is sigma of 4 is 6. Sigma of 6 is 3 and sigma of 3 is 1. So we can write the cycle as 1 image is 2, so 1 comma 2. Image of 2 is 5, so 2 comma 5. Image of 5 is 4, so after 5 we write 4. Image of 4 is 6, so 4 comma 6. Image of 6 is 3, so 6 comma 3. And sigma of 3 is 1, which is starting element. So it is 1, 2, 5, 4, 6, 3. So given permutation is a single cycle of length 6. Now second. Now starting with 1 again, here sigma alpha of 1 is 3. Then alpha of 3 is 1. So As 1 goes to 3 and 3 is again going to 1 itself, we get a cycle of length 2, namely 1, comma 3. Now the elements which are not covered in this cycle are 2, 4 and 5. So we start with 2 now. Now alpha of 2 is equal to 4. Now alpha of 4 is 2. So again here we get the cycle 2 comma 4. That is another cycle. Now the number not covered in these two cycles is 5, which is mapping to itself. So it is a single cycle. So we are getting actually 3 cycles: 1, 3, 2, 4 and 5. So we can omit the cycle 5 because it has length 1. So finally alpha is equal to 1, 3, 2, 4, and this is a composition of two cycles which are disjoint because they do not have any element common. Now third is already written in the cycle form, but it is not in disjoint cycle form, because if you observe first and second cycle, 4 is common, 2 is common. So what we will do, first we write beta as a composition in array form. We find that composition and then we express it in cycle form. Now the maximum number here is 7. So it is a permutation on 7 symbols. So writing all these three permutations in array form and then finding composition we get. So this is 4 to 1 5, which we have written in this array form. This we have written here in array form, and 5 6 7 1 in array form. Now do the composition from right to left, top to bottom. So 1 goes to 5, 5 goes to 5, and again 5 goes to 4. So finally 1 goes to 4. Same way 2 goes to 2, 2 goes to 6, and 6 goes to 6. So second element is 6. So in this way we get beta finally in array form. Now we write in cycle form. 1 goes to 4 and 4 goes to 1. So first is cycle of length 2, 1, 4. Now the element not covered here is 2. So we start with 2 now. 2 goes to 6. So 2 after 2 we write 6. 6 goes to 7. So after 6 we write 7. Then 7 goes to 5. So 7 5, and 5 goes to 3. So we write 3. Finally 3 goes to 2 starting element. So here we will close the bracket. Now if you observe these two cycles, no element is common. So we have expressed beta as a disjoint cycle form. Composition of disjoint cycle form. Now these are some theorems on permutations. Every permutation can be expressed as a product of transpositions. To write the permutation as a product of transpositions means cycle of length 2. We first write it as product of disjoint cycles, and then we write each cycle as product of transpositions as follows. So if it is a cycle I1 I2 IR of length R, then we write it as I1 IR means first and last element, then first and second last, like I1 IR minus 1 and so on, I1 I2. If a permutation in Sn is a product of R transpositions and also a product of S transpositions, then Rs are either both even or both odd. Now what is the meaning of even and odd permutation? A permutation sigma in Sn is called as even permutation if sigma is a product of even number of transpositions. So if it is possible to write sigma as a product of even number of transpositions, means 2, 4, 6, 8 like that, then it is even permutation. And if sigma is a product of odd number of permutations, then it is an odd permutation. If a permutation is a cycle of length r, then its order is r. Further, if a permutation is a product of disjoint cycles of lengths R1, R2, Rk, then its order is LCM of R1, R2, Rk. Now this theorem gives us how to find order of permutation. So if it is a permutation of single cycle of length R, then directly we can say that its order is R. But instead of single cycle, if it is a product of disjoint cycles of length R1, R2, Rk, means it is a product of k disjoint cycles with length R1, R2, Rk, then order of that permutation is LCM of all these numbers, that is R1, R2, Rk. Now, here in this example, we have to decide whether given permutation is even or odd. Also, we have to find its order. Now, first is sigma. It is a permutation on 9 symbols. First, we express it as a product of disjoint cycles. So, 1 goes to 2, then 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 1. So here cycle gets completed. So we have written this part. Now the element not covered here is 6. 6, 7 both are mapping identically. So we can write it as cycle of length 1. And finally 8 goes to 9, 9 goes to 8. Now we omit 6, 7 which are cycles of length 1. So this is 1, 2, 3, 4, 5, 8, 9 which is a product of disjoint cycles. Now, to find its order and to decide whether it is even or odd, we express it as a product of transposition. So, 1 5, then 1 4, 1 3 and 1 2 and 8 9. So, all these are cycles of length 2. It means all are transpositions. So, how many transpositions we are getting here? 5, which is an odd number. Hence, this permutation is odd. Now, we have to decide its order also. Now, sigma is not a single cycle. So, here to find its order, consider all these cycles. Now, each cycle is of length 2 here. But we can't consider this part actually, because whenever we have to find the order of the permutation, we have to consider that permutation expressed as a product of disjoint cycle. So instead of considering this final part, we consider the previous step where we have expressed sigma as a product of disjoint cycles. So here it is a cycle of length 5 and here it is a cycle of length 2. So, as it is product of disjoint cycles of lengths 5 and 2, its order is nothing but LCM of 5 and 2, which is 10. So, order of sigma is 10. Now, second is this permutation. Already it is written as product of cycles, but again they are not disjoint because here 6 is common. Now first we express them in the form of array notation and then taking the composition, finally we get single cycle in single permutation in array form. Now writing in cycle form we get 1 2 6 7 and all these are cycles of length 1. So finally it is 1 2 6 7, a single cycle of length 4. Now to find whether it is even or odd, we need to express it in the form of product of transpositions. So it is 1 7 1 6 1 2, which is the product of 3 transpositions, which is an odd number. Hence this is again an odd permutation. Now what about its order? We have expressed the given permutation as a cycle of length 4 and so its order is 4. Now the third one, again it is written as a product of some cycles but that is not in disjoint cycle form. Now the maximum element is 4, so each is a permutation on 4 symbols. So first we write each cycle in array form, then taking the product or composition we get this single permutation in array form. Then here we have expressed it in the cycle form, which is a cycle of length 3. Then it is 1 3 1 4, which is transposition. So there are two transpositions, so it is an even permutation. And as it is a cycle of length 3, its order is 3. Again in this case, in the same way, we have to check whether it is even or odd and also we have to find its order.